given little a, little b integers. Capital A is all integers, so that little a divides x. Capital B is integers, so that little b divides x. And what we need to show is that A is a subset of B if and only if B divides A. So everything in black is given. It does not change, but we know for an if and only if, this is our P and this is our Q, and we have an if and only if statement. So we need first this direction, P implies Q, and I'm going to do both directions directly. Okay, so we assume A is a subset of B, and we need to show little b divides A. Well, the first thing to observe is that notice that A is an element of A. And the reason is, maybe I'll put it in blue here, is that A divides A is clearly true. A times 1 equals A. Okay, so this is justification for why little a is an A, and then since capital A is a subset of B, we also have, just looking at this definition tells us that B divides A. Or maybe I should say it in two steps. We would say that A is an element of B, that's the definition of subset, and then comma, this means little b divides A. And that's the end of this direction. So now we have the other direction to prove, and then we will be finished here. So we assume that B divides A. And we want to show that A is a subset of B. To show A is a subset of B, we take an element of A and argue why it is an element of B. Okay, well, since X is an A, let's unravel the definition. There exists a Y and Z with, well, we know that A divides X, so A, Y equals X. Now we need to jump into X being in the set B, and if you look at where you're trying to go, you're trying to get that B, little b divides X, or there is some integer, so that B times that integer equals X. And it may not be obvious yet, but you see, if you are stuck, we have not used the assumption yet. So the assumption tells us there is another integer, say W, with B, W equals A. And now we are in really good shape because we can just substitute BW in for A. So then we have the following. If you stick this in for A in this equation, we have BWY is X. And now watch me group this, okay? And look, this is what we want. This shows, which means B divides X as WY is an integer and we have showed that A is a subset of B. And this completes the proof of the if and only if. I'd like to prove the following. If you have three sets, here you take A minus B, this is the set difference, and then U minus C, this is the same as A minus B union C. And if you do a Venn diagram for either one of them, you will get this picture. you can either think about this as, this white circle together with this white circle is the union, and I've taken everything in A minus the union, or that's the right-hand side, or first we would have A minus B. Okay, everything in A minus B is the green and red shaded. Then you take everything in A minus B and you subtract off the elements that are in C, and we are left with exactly this green region. Okay, but the problem is not to illustrate this equality with a Venn diagram, it's to prove it using logic and set theory. So let's do that. So I will first, to prove equality of sets, I need the subset in one direction, and then I need the subset in the other direction. So going in this direction, we will let X be in this. Now let's unravel what this means. Okay, so then X is in A minus B, and X is not in C. Okay, and then we will unravel one more. So thus X is in A and X is not in B, and X is not in C. Okay, now at this moment I want to bring some logic into it. Okay, so we're going to keep X being in A. So we know not X in B and not X in C is logically equivalent to, okay, let's see, well, it's going to be not X is in B or X is in C. This is using De Morgan. Using De Morgan's law. One of them. The De Morgan's law that I'm using, maybe I'll put it on the board. This is for Boolean algebra. It says that if you negate a union, you negate this, and you negate this. This is the De Morgan's law that I'm using, except I started with not and a not and an and I turned it into the negation of a union. Okay, very good. Well, this means, now let's go back from, this sort of Boolean algebra statement to what that means about the sets. So this means X is not in B union C. And we have not affected this, so we have X is in A. X is not in B union C. So therefore, X is in A minus B union C. Now, the other direction, in a sense, maybe I will take the time to write it. I'll do it in another color, but it's going to be identical because everything I've said has been equality. It's not been an implication. These two are equivalent, and we could just take it and read it in the other direction to get the inclusion the other way, but perhaps I will write it so that we do have both directions of the proof. So now, B in A minus the union, and then X is in A, and X is not in B union C. Now let's go back to logic. So we have, it's not the case that X is in B or X is in C. This is the definition of, not being in a union. Here's the union, okay? Again, I'm using the exact same De Morgan's law. I'm just going in the other direction. So this is equal to logically equivalent to not X is in B and not X is in C, which means X is not in B and X is not in C. Okay? So now let's put everything together. We have X is in A. We have X is not in B. This means X is in A minus B. Now one more. Let me add a color. X is not in C. X is in A minus B minus C. And this direction is complete. Okay? I'll put a little box. So this, the two arguments were almost identical. One went down and one went up in a sense. But this, we have a complete proof here of the fact that these two sets are equal. For sets A and B, we want to prove that A union B equals A intersect B if and only if A equals B. And this is an if and only if proof, so we have two directions to prove. And I will try to illustrate some different proof techniques as we go about. So first of all, let's prove this direction. Now, we have a P, if and only if, Q. And just for the sake of practicing different things, as I mentioned, I'm going to prove this direction, which would be P implies Q, as a contrapositive. So here we go. By contrapositive, well, we assume not Q, assume A is not equal to B, and then what we want to show is that A union B is not equal to A intersected with B. Okay? Now you could potentially prove this directly. For me personally, I thought contrapositive first when I was working through it. And so that is what I'm going to present to you. Okay, so if A is not equal to B, means one of two things. Number one, there exists an X in A with X not in B, or there exists an X in B with X not in A. This is what it means if you have two sets and they're not equal, then there's either something in here that's not in here, or there's something in here that's not in here, or maybe both. But in any case, now for this first one, maybe I will keep with blue. there's an X in A that's not in B. Well, X in A means that X is in the union. And X not in B means that X is not in the intersection. Okay? And the other one is almost identical, because if you have something in B, watch, all I'm going to do is interchange X and B, A and B, excuse me here. If you're in B, you're in the union, and if you're not in A, then you're not in the intersection. So in either case, and the argument was very similar, so we see, or in either case, well, in either case, and maybe I will get another color to underline, we have an element in the union, and that element is not in the intersection, so therefore, the union is not equal to the intersection. A union B is not equal to A intersect with B, and this is the contrapositive. So we have shown this direction by contrapositive. So now I need to do the other direction. This is Q implies P, okay? And we will do this one directly. Assume A equals B, and we want to show A union B equals A intersect B. This is a direct proof. Assume this and show this, okay? Now, one thing that we should be able to see is there's always, to show two sets are equal, you must show that the set on this side is a subset of this one. The set on this side is a subset of this one, because equals is really two subsets. We would need this way, like I said, and we would need this way, okay? But, the intersection is always a subset of the union, and in fact, it comes from something we discussed in class when we first discussed the intersection and union. So, but we need to make a comment about that, otherwise our proof would not be complete. So you might just write, we know that the intersection is always a subset of the union, as, for example, we showed or discussed A intersect B subset of A, always. And then we also showed and discussed that this was always a subset of the union. And then one of the exercises you had in this homework is that the intersection, if you had, well, it was listed for three sets. A subset B subset C, then A is a subset of C, like this, okay. In any case, this statement holds, okay? Now, to get equality, we need the other direction. So I need to show that the union is a subset of the intersection, and I will have that A intersect B is equal to A union B. Okay, so we take something in the union, and we need to make some argument about why X is in the intersection. So this means that, or X is in B. We have these two possibilities. Now, we have to go back to our assumption. Our assumption here is that A equals B. So, well, A equals B. I'm just trying to find the best way to say this. Since A equals B, comma, X is in A means X is in B, and this was an or. If X is in A, X is also in B. They're the same set. If X is in B, X is also in A. They're the same set. So in either case, we see X is in both of them. X is in A and B. X is in A and B. And this completes the proof. You might just put a comma, which shows that the union is a subset of the intersection, and in fact it shows that they're equal. Okay,